Welcome back to another physics problem. In this problem, we're going to look at conservation of energy. This is example 3 from 4.7, conservation of energy. And let's get started. Machine loads a pinball, so we're given the mass. Uses a spring with a spring constant of 10.2 Newton meter per meter. We're given K. While drawing the spring back 4 centimeters. So this is the displacement in the spring. Of course, your pinball playing fields are not flat. When it reaches the end of the field, the pinball hits the back wall with 1.2 meters per second. This is some form of velocity. I am going to call this the final velocity at the very end. How much energy was wasted, and if the wasted energy mainly came from friction, what was the friction force? In here we have a diagram. The height from the bottom to the top here, this is 5 centimeters. The length of the field is 20 centimeters. Before you start an energy conservation problem, I recommend pick 2 points in the motion or in the process in which you're interested in. I am particularly interested in when the pinball compresses the spring. As my first point, I'm going to call this my initial point. And what I'm interested is at the very end when the ball hits the wall. This is my final. Why am I interested in this? Because I want to find how much energy was wasted in this entire process. Not just from when the spring was compressed to when it's released, but from when it goes from the bottom all the way to the top. Initially, we have elastic potential energy. I'm going to call this ES for E spring. Okay, so ES is 1/2 kx squared. So we have initial elastic potential energy. We do not have kinetic because the ball starts from rest, as you've maybe have played pinball before. EK is 0. And I'm going to call the reference point for height to be 0 at the bottom. And since height is 0, we have no potential energy as well. At the end, final, we have a ball going up 5 meters high. So it does have potential energy. And at the end, in the question, it says the pinball hits the back wall with 1.2 meters per second. That means it has kinetic energy. It doesn't have elastic potential anymore because it's no longer by a spring, no longer compressing or extending a spring. So here I've laid out my 2 positions of my motion, identified my energies. I'm going to draw a little schematic to kind of show us what's happening. From initial to final, we know that some energy was being lost. Now, going back, when we talked about these arrows, the reason why I showed these arrows is to show us how the equation works from a visual perspective. I'll draw one here so you can see what I mean. In the beginning, we have this much spring energy or elastic potential energy. Okay, while the ball is going up to the top of the field, we know that some of that energy is being wasted. And I'm going to draw part of my arrow leaving my system. This is my E energy that's being lost. By the way, you do not need to draw this when you're doing a problem. I'm just doing this so you can see what's happening. Some of that energy gets turned into kinetic energy. Of course, the width of my arrow will tell me exactly how much energy in proportion is going into each form of energy, but I don't have that number right now. But let's just say that this much of my energy is going into kinetic. And as a result, what's remaining is this portion, and I'm going to draw like this so it's not interfering with the other ones. Some of it's lost, some of it is converted to kinetic energy final, some of it's kinetic to gravitational potential energy final. Everything else is lost. This is how much energy I started off with, E initial. The only energy I had in the beginning was elastic potential energy. So you can see that I have elastic potential energy to start with. That gets converted to kinetic energy, good amount of potential, or not so much potential depending, and a good amount of it is lost. Now, of course, my widths would be proportional to the exact amount of energies, but you can see the idea of how if I add up all the energy I have in the beginning, that should equal to every energy that you see here when the ball reaches the top. So just from this diagram, in terms of the width of the arrows, my ES, elastic elastic potential energy in the beginning is equal to my EK final plus my EP final plus my E lost. You might be wondering, Miss Lee, that's different from your notes. You had E lost or work on the other side. What I can do is I can move this to the other side, and this becomes ESI minus E lost equals EKF plus EPF. Remember, when we talked about work or energy that's being gained or lost, we say that the work is negative. You expect to see this negative sign if work or energy leaves your system. It's positive if energy enters your system, and is not the case for this question. So the negative here should make sense. It's the exact same equation, but rearranged. Now we have the base equation, and again, as long as you understand conservation of energy, you should not need to memorize any equation. What I've done here is I laid out the concept behind conservation of energy, and that concept should drive how you form your equations in your questions. ESI, I'm going to put in everything now. I have 1/2 kx squared. This is equal to, minus my E lost, and this is going to be the one I'm losing due to friction. 1/2 mv final squared plus mgh final. And I'm going to write down all of my values that, just so you may have forgotten. K was 10.2 Newton per meter. My X was 4 centimeters, but remember, this must be converted to meters. I'm not going to care about significant figures right now. Mass, 5 grams, or 0.005 kilograms. Final velocity, 1.2 meters per second. G, we all know what G is. HF, this is 5 centimeters or 0.05 meters. Now what I need to do is I just have to put every number in my equation, that's it. And find E lost. This part should be very easy. Forming the equation would be the hardest part. Well, let's solve for E lost. I am going to put E lost to one side of the equation, or I could do this. This is just doing the math. Okay, so I'm moving this term to the other side. I'm left with negative E lost equals to 1/2 mv final squared plus mgh final minus 1/2 kx squared. Okay, I don't care about that negative sign for now. We could just leave it there. Let's just put in all our values. 1/2 mass, 0.005 times final 1.2 squared plus mass again, 0.005 times gravity. You don't need the negative sign here because we're talking about energy anyhow. The height, 0.05 minus 1/2 10.2 for spring, and the displacement, which is 0.04 squared. After you have everything, you substitute in everything properly, you should have 0.0021 joules, or 0.0021 joules. This is negative E lost, or that's the energy that you lose. There's probably a negative sign in there. Okay, but anyhow, the negative just means you're losing energy. If the question is already talking about energy loss, you don't need to have the negative sign. If you're talking about energy in general and there's no indication whether or not you're losing or gaining that energy, it might be helpful to write in that negative sign or to indicate that this is how much energy that's being lost. Okay, so that's part A. I'm gonna end my video here. So this is part A. I will do part B in a separate video. All right, and I will see you back shortly. Bye now.